Okay, in chapter 6, we're going to be talking about another cause of cancer, radiation. And I should point out up front, radiation is an interesting example because, as we'll discuss here, it can cause cancer. But of course, radiation treatment is also used to treat cancer because of radiation's ability to kill dividing cells. And so when you hear that term radiation, it's kind of a charged word. At least to my mind, first thing I would think of is, nuclear radiation, maybe some kind of weapon that might be using radiation or some type of, new scientific discovery. Um, but really, our main exposure to radiation is just going to be through visible and ultraviolet light, because radiation is just simply defined as energy traveling through space. And so you have this whole electromagnetic spectrum ranging from, very high energy damaging gamma rays, as we'll discuss, things that have a very low wavelength, um, to low energy, high wavelength things like radioactivity or microwaves. But we are constantly being exposed every day to radiation in the form of visible light and UV light. And as I'm sure you're aware, let me just go back here one second. Uh, there has really been no evidence linking some of these lower energy forms of radiation, basically visible light and below, to cancer in any way. But UV, X-rays, gamma rays certainly have. We do see that link. And I'm sure you're aware of the fact that UV light, UV radiation has been linked to skin cancer primarily. And there's tons of data supporting this, but even just very simply on a basic epidemiological level, if you look at the United States and parts of the country that have the highest sunlight intensity, so here, darker orange or red are going to be the sunniest parts of the country. Um, we see increased skin cancer rates in those places as well. And in these little graphs here, they're looking at two different types of skin cancer, squamous cell carcinoma versus basal cell carcinoma. But yeah, increased exposure to sunlight, UV radiation is going to increase your skin cancer risk. And we'll get into some of the details on this. So if we think of those two different types of skin cancer, and really there's three main different types, um, we've got basal cell carcinomas, the squamous cell carcinomas, and then melanomas, melanomas being the scary ones. So I'll get into in some more detail. But what are these different cell types? Well, you have the basal cells are the dividing cells. And they're basically growing on this basal lamina. Um, and as these cells divide, uh, the the cells that are being produced are pushing cell layers up towards the surface of the skin, and as cells migrate, they're basically differentiating into this scaly squamous cells, that outer layer of skin cells that are essentially dead cells that are constantly being shed. Um, so obviously the squamous cell cancers are going to be those in these upper layers of skin cells. Basal cell carcinomas are going to be in that basal layer. But the ones that are the most concerning are the melanomas, and those are when the melanocytes become cancerous. And you can see melanocyte here, sort of a tendrily type cell that produces the melanin pigment, right, that actually can absorb some of that UV energy and provide protection. And so by far the vast majority of skin cancers are basal cell or squamous cell carcinomas. Melanomas account for a very small percentage of annual skin cancer cases. But because they have proven to be very hard to treat, um, they don't respond well to standard treatments, radiation, or chemotherapies. They do account for the vast majority of skin cancer deaths. And Interestingly, these non-melanoma type skin cancers, the basal cell and the squamous cell, you tend to see those arising primarily in people that are exposed to sun on a regular, more constant basis, which is sort of what we were looking at in the previous data with the map of sunlight exposure in the US. Whereas you tend to see melanomas in people that just get very intense periodic exposure to sun. So, the person that's very fair skinned and, goes to the beach once a year and gets a bad sunburn. And or in people that, got bad sunburns when they were young. A lot of times you'll see melanomas on either the back or on your legs, places where you may forget to apply sunscreen. If we zoom in on the different types of UV, there's three main types of UV light. So there's UVA, UVB, and UVC. And UVA light has the longest wavelength. Remember, the longer the wavelength, the less energy associated. And UVA doesn't get filtered out at all by the Earth's atmosphere. So it's not thought to damage DNA the same way that UVB can. Uh, but there's a lot of data showing that it is acting as a promoting agent. Remember, that's really anything that's going to stimulate cell proliferation and is an important part of carcinogenesis. UVB, higher energy, it does get partially absorbed by the ozone layer. This is one of the reasons that we have worried about ozone depletion. But UVB is what seems to be causing the majority of DNA damage, as we'll talk about. Primary cause of sunburn, tanning, linked to aging, and this is what's primarily tied in with skin cancer, although UVA does contribute as well due to its act as a promoting agent. And UVC, even though it's the highest energy, is actually completely absorbed by the Earth's atmosphere, so we don't worry about UVC in terms of our cancer risk. So how does UV exposure cause cancer? Well, what happens is that the energy from the UVB primarily is being absorbed by your skin cells, and then by the DNA, specifically by the nucleotides in the DNA in those skin cells. And what will happen is in places in your DNA where you have two pyrimidines next to each other on a single strand of DNA, so two C's or two T's, are particularly adept at absorbing that energy, and it'll cause the formation of a covalent bond between those two adjacent nitrogenous bases. And remember, normally nitrogenous bases next to each other are not directly bonded to each other, so they're bonded back to the deoxyribose sugars, and then those sugars are connected to each other by covalent bonds. But here we're directly causing the formation of a new covalent bond between those bases. That's going to cause a distortion in the single strand of DNA. And when we go through a round of DNA replication, the strand on the right here that had the two guanines is going to be just fine. DNA polymerase can read that and replicate it appropriately. But the strand now with the dimer, the pyrimidine dimer, DNA polymerase doesn't know how to deal with that, and it will try to pair it up with two adenines instead of two guanines, as it should. And so then if we go through another round of DNA replication, we would basically cement this change from a CCGG pair to a AATT pair, and that would be then considered a permanent mutation. And there's tons of data showing that these kind of dimers, pyrimidine dimers, are very prevalent and seem to be the primary cause of skin cancers. So for example, if you compare skin cancers versus other internal cancers and look at, well, how common are these CC to TT transitions, basically what we were just talking about here, right? We went from a CC to a TT. We see they're very prevalent in skin cancers, but very rare in internal cancers, where if we look at just like single C to T transitions that would be due to other types of mutation, not dimer specifically, we almost never see those in skin cancer, or at a much lower rate compared to internal cancer. So what that's suggesting is that uh, these dimer-based transitions are much more specific to skin cancers. And another big player in this whole process is the p53 gene, p53 protein, which we will dig into in some more detail in some later chapters. But this is a gene that is mutated in lots of different types of cancer, but very, very commonly in skin cancers. And I did mention this briefly in a previous chapter, but p53 protein functions by promoting apoptosis in response to DNA damage. So it's part of that apoptosis pathway. And in fact, sunburn is believed to basically be a p53 mediated mass apoptosis event, right? So as your DNA is damaged, you accumulate all these thymine dimers. Your cells decide, oh, it's too much to repair, so they activate this p53 mediated apoptosis pathway. Those cells die, and your skin peels off, uh, and it itches and hurts and is uncomfortable. Um, but when this becomes a problem as well, what if the p53 gene itself is now mutated, right? Accumulates thymine dimers. Then that apoptosis process is no longer working. And so you could have a situation like this. So, here's your healthy, normal skin cells. You get too much sun exposure, accumulate these pyrimidine dimers in the cells in purple here. Um, and the cell in red here now accumulated mutation in the p53 gene itself. So your cells sense, yep, this is too much to repair, so they kick on that apoptosis event, that sunburn uh, cell death event. Um, the majority of these cells now die and disappear, but of course the one that had p53 mutated does not, because it can no longer undergo apoptosis. And as those cells die, they need to be replaced. So we may be kicking on cell proliferation, right? Think UVA coming in and acting as a promoting agent as well. So this cell with the p53 mutation may now divide to help fill in some of these gaps. So now you've got multiple cells with p53 mutations, right? You imagine this happening uh, round after round, and you're accumulating more and more mutations in these cells now. They can't undergo apoptosis, and eventually you're very likely to get to the point where those cells become cancerous. All right, so what about tanning, right? We tend to think about tanning as a healthy thing. It's attractive to have a tan. Um, and the bottom line is dermatologists will tell you, any sun exposure, even if you're not being sunburned, just normal tanning is not good, right? You're accumulating these dimers, you're damaging your DNA in those cells, and it's contributing to cancer risk and to aging. Um, so, the more you can avoid sun exposure, the better. Now, what about tanning beds? Tanning beds primarily use UVA, which remember was the lowest energy form of UV light. So you might think, well, they should be fine. Uh, but no, in fact, tanning beds are linked to increased cancer risk, and they've been classified as a group 1 carcinogen, and this group includes things like plutonium and radium. So uh, definitely not something you probably want to intentionally expose yourself to. World Health Organization has said that tanning beds pose a serious cancer risk. And you have seen some legislation basically trying to limit the use of tanning beds by minors. Um, but we definitely haven't seen the embrace of regulation as you have with, say, cigarette usage, cigarette consumption. And so, of course, another part of this whole equation when it comes to tanning and tanning beds is that your risk of cancer depends a lot on your particular skin type. So you have these 6 different skin types, type 1 being, super pale, technically considered as melanocompromised, very fair skinned. You basically won't tan and just would go straight to the sunburn, versus skin type class 6, who's going to have very dark black or brown skin and have very low risk of burn and low risk of skin cancer as well, because the increased amount of melanin, right, is absorbing some of that UVB energy and protecting the DNA in those skin cells. But bottom line, try to avoid sun exposure as much as you can. Cover up, wear your sunscreen if you are going to be out in the sun. Okay, so for sure, UV light has been linked to skin cancer. What about some of these higher energy forms of ionizing radiation, X-rays or gamma rays? Well, X-rays have been around since the late 1890s, late 1800s. They were first discovered by this guy Wilhelm, and I'm going to skip the video on how X-rays work, but you can always Google that if that's something you're particularly interested in. But there was a lot of excitement upon the discovery of X-rays. Even Thomas Edison got in on this and was working pretty heavily on X-ray technology until his research technician, that was the one primarily handling these machines, became the first person to die of X-ray exposure. But early on there was so much excitement. People were making what were called bone portraits. They basically go get X-rays taken to their hands or something, just because it was a novelty. Shoe stores were using X-rays to try to help fit shoes properly. But as the danger became realized, of course, it stopped being used for some of these more frivolous purposes, and was basically only being used in medical situations, which is still how it's used today. And as we'll talk about, there still is some danger associated with X-ray exposure, but we do still use it because the medical benefits in most cases is going to outweigh the minimal danger of limited exposure. And so just to give you a feel for dosage, there's a couple of different ways you can measure radiation dosage, typically either in grays or sieverts. Those are equivalent units. But a typical chest X-ray, for example, which is actually a pretty large medical dose, is 0.00008 grays. And just to give you a feel, in studies with mice, which keep in mind have a relatively short lifespan to begin with, they're looking at life shortening in number of weeks tied to radiation dosage. That dosage associated with a typical chest X-ray is going to be way, way, way down here at the very bottom of the scale. So the risk associated with those low dose exposures is going to be quite minimal, but not negligent. And then, of course, there's other types of radioactivity. You've got particulate radioactivity like alpha or beta particles, nuclear radiation. And keep in mind, these are basically subatomic particles being released by atoms that are unstable and are throwing off these particles and decomposing over time. So famously, radioactivity was first discovered by these two scientists, Henri Becquerel and Marie Curie. Marie Curie, of course, died from radiation exposure from carrying around radioactive rocks in her lab coat for a number of years. But of these three main types of nuclear radiation, you've got alpha particles and beta particles. Alpha particles have a positive charge, 2 neutrons and 2 protons being released by atoms. Beta particles have a negative charge, it's just straight electrons being released. And then gamma rays, there's no charge, so there's actually another form of electromagnetic radiation that has an even shorter wavelength, so higher energy than X-rays. And out of these, really the most damaging, the main concern tends to be focused on alpha particles. So those are 20 times more damaging than X-rays. But because they are quote-unquote large, relatively large particles, as I said, 2 protons and 2 neutrons, they don't penetrate tissues very well, so there's not a whole lot of risk, especially at the low doses that you might encounter in normal day-to-day life. There's not much risk in alpha particles coming from outside the body unless you're exposed to a very large constant dose. However, inside the body, alpha particles can be extremely damaging, and you might say, well, okay, I'm not going to put alpha particles inside my body. But I don't know if you're familiar with radon gas. So this is a gas produced by the breakdown of uranium in rocks, so just naturally produced. And there's certain parts of the country where radon tends to be a bigger problem. You can see those in red here. So here in southeast Kansas, where it's sort of moderate risk, and tends to be more of a problem if you're subterranean. So for example, if you have a house with a basement where you're spending a lot of time, if you lived in one of these areas where radon was an issue, you could be getting too much exposure. But basically the deal with this is, so you get this radon gas that does contain alpha particles, and it is actually getting converted into polonium, which is this tiny metal that can lodge, you can inhale and can lodge in your lung tissue, where it continues to release alpha particles. So in that case, you would have a source of alpha particles inside your body, which could greatly increase your risk of lung cancer. So they do make radon detectors, sort of like a smoke alarm that you could put. Usually people put them in their basements just to see what their radon levels are. And I think if you do have a radon problem, there are certain types of remediation that can be done to reduce the exposure inside your home or workplace. And there's some interesting data in terms of exposure to high doses of radioactivity that have primarily come from survivors of, nuclear blasts, either nuclear bombs or nuclear reactor meltdowns, like Chernobyl. And in these types of, high dose exposures, people are being hit with alpha, beta particles and gamma rays. And so here's some data that they collected. These were from survivors of the atomic bomb blasts in Japan at the end of World War II. And what you're seeing here is that these high-dose exposures are basically increasing risk to all types of cancer, some more than others, primarily leukemia, and interestingly, cancer of the larynx, esophagus, pharynx. So presumably that's because people were breathing in the radioactivity in those cells in the throat, upper respiratory tract, were those taking the brunt of the hit in most cases. So we see this increased risk with increased radiation dosage. And in terms of cancer deaths, they're a little bit all over the board. And some of this variation may just depend on, aggressiveness of specific types of cancer, difficulty in being able to treat those specific types, or tendency of those to metastasize. But here you see this other unit of measurement for radioactivity, sieverts instead of grays, but they are equivalent, as I mentioned before. Another interesting thing that was observed from this data is that you saw a pretty linear increase with cancer risk in both leukemia and most of the solid cancers with increasing radiation dosage until you got to this about 3.5 sievert dosage, in which case cancer risk drops way back down all of a sudden, and then if you get above that, it climbs back up. So what's going on here? Well, I think that dosage, 3.5 sieverts, is what's causing cell death. So at that point, because the irradiated cells are dying, right, that actually reduces cancer risk at that dosage. But once you get beyond that, you've killed off cells, but then you're further irradiating additional cells, and cancer risk climbs back up again. So I guess the moral of this story is, if you're going to be exposed to a massive dose of radiation, you want to get exactly 3.5 sieverts, and no more, no less. So keep that in mind. All right, so what kind of DNA damage are you getting from these higher energy types of ionizing radiation? Well, these are called ionizing radiation because they'll strip electrons away from molecules in cells, create these reactive ions. And of course, in cells, you've got lots of water molecules, so you tend to get lots of these hydroxyl radicals that can then attach to nitrogenous bases, as you see happening here, or cause the removal of bases altogether. So either of those is undesirable and is going to lead to more permanent mutations. And then if you have enough energy, you can actually cause breaks, either single-stranded or double-stranded breaks in DNA, which may or may not be able to be repaired accurately, and can again cause, even if they are repaired, can cause accumulation of additional mutations. So what is our typical exposure to radiation? And by far the vast majority is going to be from natural sources. The biggest slice of the pie here is radon exposure, but you've also got cosmic rays, other forms of terrestrial radiation. I'm not sure what's going on here. Internal body is more than 10%. Not sure exactly what they're referring to there. But you've got less than 20% that's thought to be quote-unquote artificial. So this would be, medical x-rays or other medical procedures that might utilize radiation in some way. And then, there may be other consumer products that contain some low amounts of radiation that you might be getting some exposure from as well. But on average, the total annual dose is 3.6 millisieverts, so that would be 0.036 sieverts per year on average. Most of that, again, coming from natural exposure. And so, obviously there are some things that we do that increase our exposure to radiation. You get a dental x-ray, maybe you live close to a nuclear power plant. Interestingly, a transatlantic flight, because you're at a much higher altitude, you're receiving more cosmic radiation. So we do these things that do increase our radiation exposure. And there's what's called the BERT, which stands for background equivalent radiation time, which is basically converting one of these doses of radiation into the amount of time it would take you to receive that same dose just from natural exposure. So tying it back into what we were just talking about in the previous slide. So for example, if you live near a nuclear power plant, you are receiving some very low dose of radiation just due to proximity, but it's going to be equivalent to less than like 1 extra day of natural exposure, so very minimal. A dental x-ray is equivalent to about 1 week of extra exposure. A mammogram, which is a little bit higher dose x-ray, about 3 months. And this is interesting, so there's actually a little bit of radioactivity in cigarettes, polonium. If you were to smoke 500 packs a year, that's a lot of cigarettes, but still it's equivalent to about 10 years of extra natural exposure. So bottom line, what I'm getting at here is the risk from these medical x-rays is pretty low. So obviously you don't want to get more than you need, but that's probably not worth stressing out about. So, one thing I get asked about occasionally is, well, what about cell phones, right? So they're using some electromagnetic radiation in the form of RF waves, is what cell phones operate on. And RF waves are found down here between radio and microwave. So, as I said, there's just no data showing that any of these lower energy forms of radiation are linked to cancer in any way. So, it's very unlikely that cell phones are going to increase cancer risk. But that being said, we do we've talked about the idea that there's often this lag between your exposure to carcinogens and or radiation and the development of cancer. So I guess it's fair to say the jury's still out on that, but we are probably getting close to 20 years of cell phone usage at this point. So I don't think it's going to be something to worry about. All right, next time we'll be talking about infectious agents, primarily viruses, and their ability to cause cancer.